Back for part two. So here we're going to look at how rate is related to concentration versus time. So in order to determine the actual concentration of reactants and products at a particular time, you have to use what's called the related rates equations. And these are equations that relate the concentration to the time, but it depends upon the order of the reaction. So, for instance, if I have a zero order reaction, okay, I know that the change in concentration of the N2O has no effect on the rate. And so my rate will just be dependent upon what the rate constant is. Because if I had a zero order reaction, my value for M is 0. I plug that in, and any value of concentration that I would put in here would be equal to 1, because any value raised to the power of 0 is equal to 1. So therefore, the rate is always equal to K. So what that means is that the decomposition of N2O is a constant rate, and it just depends upon how long it runs for. So my related rate equation, so the first, I'm skipping over some details here, but you can go back and read them. My related rate equation for a zero order reaction, this says first, it should be 0, would be this, that the concentration of the reactant after any period of time, so we could say the concentration final, is equal to the initial concentration minus K times T, because it all depends upon is how long the reaction progresses for and what the rate constant actually is. Okay, so now we'll go on to the first order reaction. So for first order reaction, I have a lot of details in here. I talk a little bit about how they use calculus. Instead of calculus, we use a logarithmic expression. And so the bottom line is that the equation in the end is really this. So for a first order reaction, the related rate expression is this: the natural logarithm of B final, whatever the final concentration is that you're going to be looking for, is equal to the natural logarithm of the initial concentration minus K times T. And so using some of the rules of logarithms, the expression it's either going to look like this expression here, or it can also look like this expression here. They're the exact same thing. Kt equals the ratio of the natural logarithm of the initial over the natural over b. So the natural logarithm of this ratio. And then though we also want to look at half-life. Typically, your half-life expressions are a first order decay process. And so if we look at that same equation that we just used on the last page, if I take the ratio of the initial concentration to a final concentration, which would be 0.5 for half-life, because half-life is the amount of time needed for an original reactant, initial, to decrease to 1/2. And so the natural logarithm of 1 over 1/2 is a natural logarithm of 2, and it's a constant, 0.693. So natural logarithm of 2 is equal to 0.693. So I can say that the T1/2 for a first order decay process, and again, this is the one that's typical, first order for half-life. So it's equal to T1/2 is equal to the constant 0.693 over whatever the K, which is the rate constant for that particular reaction. Right, and then the second order related rate expression is this. It's 1 over the concentration. So 1 over the final concentration is equal to 1 over the initial concentration plus KT. And so essentially what you're going to learn in the lab that you're going to do this week is how can we use graphing of data to determine the order of a particular reaction. So what we'll find out through the lab that we're going to do is that for a zero order reaction, any plotting of X versus T would lead to a linear graph. If it were a first order reaction, it would be a plot of the log of the concentration versus T. Here I have log base 10, but we'll actually use natural logarithm of X. And then for a second order, it would be the inverse of the concentration versus time. So if you're trying to determine an order from a set of data, you can always do these three plots of X versus T, natural logarithm of X versus T, and the inverse of X versus T. And whichever one gives you the linear relationship will identify what the order of the reaction is. I've put it here, and you'll also find this in Blackboard content shell. This is a summary. This is a really nice resource to have for when you're doing your problems and when you're taking your test. But it gives you all of the information, kind of summarizes it all in a table. So here's the graphs that I was just talking about. So if it were a zero order reaction, my graph of concentration versus time would look like this. The zero order would give you a negative slope. The natural logarithm versus time would also give you a negative slope. But if it were first order reaction, it would be a linear relationship there. And then the inverse of concentration over time for the second order reaction would give you a positive slope. And so this gives you kind of a sample set of data that we talked about early on. This would give you the half-lives. This is the one that we talked about because that's the most common, although you can have half-life with other orders, but that's the most common. And then this is always very handy. What are the units for the K value for a zero first and second order? I'm going to stop there.